Welcome friends to this lecture on computed power system analysis. We have been discussing about the modeling of YG Y0 transformer. So, we have first taken this particular transformer connection, this is the circuit diagram, this is the vector diagram, and then we have taken the loop currents, and then we have written two KVL equations. One KVL equation is A1 in the loop A1 C1, another in the loop B1 C1, and then after getting these two KVL equations, we have solved them, and after solving we have got the expressions of I1 and I2, and from the expressions of I1 and I2 we have also got the expressions of IAS, IBS and ICS, and this IAS, IBS and ICS they are already shown in this vector diagram. So, then therefore, if I now translate this IAS, IBS and ICS, so then therefore, they, if you can see, they are actually entering this I mean these three currents IAS, IBS and ICS, they are actually entering the neutral point from the terminal. So, then therefore, IAS, so then therefore, IAS we can write down, we can actually show that IAS would be in this direction. Similarly, IBS would be in this direction because they are entering, and ICS would be also in this direction. And in the primary side, our current direction would be IAP, this would be I capital BP, and this would be I capital CP. Now, according to our convention, or rather according to our dot convention, so now therefore, in this winding there is a current ICP which is going in this direction, which is going into the dot terminal at the primary side, whether the current at the secondary side is also going into the dot at the secondary side. But as we have already discussed in the last lecture, that essentially the dot convention is that the current entering the dot terminal at the primary side and the current leaving the dot terminal at the secondary side, they are in phase. So, then therefore, these two currents are antiphase in each other. So, then therefore, we can say that IAP, so then therefore, I can say that at the primary side IAP is equal to minus IAS, IBP is equal to minus IBS, ICP is equal to minus ICS. So, then therefore, IAP is nothing but minus IAS, and IAS is equal to I1. So, then therefore, it is equal to minus I1. So, then therefore, utilizing this, so then IAP is equal to I1, IAS is equal to actually minus I1, IBP is equal to minus IBS, means that I2 and ICP is equal to minus ICS, means I1 minus I2. So, I1 minus I2. So, if I now write down, so now we have got these 6 currents, now we have to only write down the equations. So, then therefore, what I have got IAP, IBP, ICP, IAS, IBS, ICS. There will be one y by 3 obviously, because every current expression has got y by 3. So, then it will also have y by 3. So, VAP, VBP, So then what? So IAP is equal to minus I1. So IAP is minus I1, and minus I1 means minus I1. So it is 2 minus 1 minus 1. So it is minus I1. So it's 2 minus 1 minus 1. So it is 2 minus 1 minus 1, and then it is minus 2 plus 1 plus 1, minus 2 1 1. So this is IAP. IBP is equal to I2. IBP is equal to I2 means minus 1 2 minus 1 minus 1 2 minus 1 I2, and then 1 minus 2 plus 1 1 minus 2 plus 1. ICP is equal to I1 minus I2, and this is nothing but minus ICS. So it is minus ICS means minus 1 plus 2. So it is minus 1 plus 2, and it is plus 1 minus 2, 1 minus 2. And IAS is nothing but just its opposite. So IAS is nothing but just its opposite. So it is minus 2 1 1 2 minus 1 minus 1. IBS is IBP opposite. So 1 minus 2 1 minus 1 2 minus 1, and ICP is also just opposite, 1 1 minus 2 minus 1 minus 1. So then therefore here again we do this partition, again here we do this partition, again here we do this partition, this partition we do, and this is y1. So this is my y1, this is y2, this is y3, this is y4, and again as we can see y2 and y3 they are transposed to each other. So this is how the modeling of YGY transformer is carried out. As another example, we will not do this detailed calculation now, because by now we have fairly understood the basic process, but we will just now go very quickly. So as another example, so let us look at that if what happens if YGY, let us say 4. So let us say YGY 4. So what we do is, again we have so we are drawing this 3 winding again, A1, A2, B1, B2, C1, C2. So and this, this, this. So this is again dot 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 dot. So this is A1, A2, B1, B2, C1, C2. So we first short them into ground. So this is phase A. So this is IAP. This voltage is VAP. So this is phase B. Voltage is VBP. It is IBP. VP, this is phase C, voltage is VCP, current is ICP. So this is what we have just now denoted. Now let us draw the vector diagram. So the vector diagram would be this, this and this. Let's say this is A1, and of course this is grounded, A2, B1, B2 and C1, C2. So this is what we have done. So now we are drawing the, now it is YUIG4. YUIG4 means A phase of the secondary side would be lagging the primary side by 120 degree, because 4 into 30 is 120 degree. So A phase of the secondary side would be lagging the primary side by 120 degree. So then therefore this would be phase A, this would be phase A, this would be phase B, and this would be phase C. So now if this is phase A, so if this is phase A, so then therefore this would be B1, B2 and this winding is C1, C2. So here also it would be small c1, c2. We should actually write them a little bit capital. So this is capital C1 and capital C2, and this is small c1, c2, and this is A1 and A2, because these two windings will be the same. So then what we are doing, we again drawing A2, B2, C2 together. So we are connecting A2, B2, C2 together, connecting A2, B2, C2, and we are not grounding the connection, and we say that this is phase A. A1 is now is actually denoted as phase C, B1 is now actually denoted as phase A, and C1 is denoted as phase B, right. So A1 terminal would be denoted as phase C, B1 terminal should be denoted as phase A, and C1 terminal would be denoted as phase B. So as usual, because here also we do not have anything, so we will take two current I1 and I2. So when we take two current I1 and I2, and then we start our journey from here. So now KVL in, so now we write the KVL equation. So we write the KVL equation in let's say A1 C1 loop, A1 C1 loop. Now at A1 this is actually VCS. So now therefore this potential should be VCS, this potential should be denoted as VBS, and this potential should be denoted as VCS. So this potential should be denoted as VCS. So what we are doing, we are actually writing down the loop equation in C1, C2. We started from C1 through C2, go to A2, then A1, and then come back, and then A1, and then come back to C2, C1. So C1, C2, then A2, A1, come back to C1. So this is the loop, or A1, A2, C2, C1, come back. So when you start from here, so it is VA1, VAS minus ZI1, Z is the impedance, and now the voltage here in this branch is VAP. So this is also in this direction, this is also in this direction. So voltage here is VAP. So this would be minus VAP, this is minus VAP. Now we are going in this direction. Now in this direction total current is I1 minus I2, so the drop is minus Z into I1 minus I2, and in this direction what is the voltage? In this direction the voltage is actually VBP, sorry, it is in this direction, so we should write it is the voltage is VAP, voltage is VBP, voltage is VCP. So in this direction voltage is VCP, but its polarity is from positive to negative here, so we are going here, so it is plus VCP because it is a rise, and then it is a drop minus VBS, so that is equal to 0. So then therefore 2Z1, sorry 2Z, so then therefore 2ZI1 minus ZI2 is equal to VAS minus VAP plus VCP minus VBS. So this is equation 1. If I now write down KVL equation in C1 B1 loop, now write down KVL equation in C1 B1 loop. If I now write down KVL equation in C1 B1 loop, so it is VBS, so VBS minus Z, in this direction current is I2 minus I1, Z I2 minus I1 minus, in this direction the voltage drop is, this reflected voltage drop is VCP, so VCP. Then in this direction the drop is current drop, that is the basically the drop due to current is ZI2, ZI2. Now in this direction we are traveling, the voltage is drop is from here to here, but it would be actually here to here. So this is would be VBP plus VBP, so it would be plus VBP minus, this is phase A, so this is phase A is VAS, VAS, VA, this is equal to 0. So then therefore minus ZI1 plus 2ZI2 VBS minus VCP plus VPP minus VAS. So this is equation 2. Solve equation 1 and 2. So once we solve equation 1 and 2, so what we do is we do 1 into 2 plus 2. So what we get? 1 into 2 plus 2. So 1 into 2 is, sorry, 1 into 2 is 4Z I1 minus 2Z I2 plus 2, plus 2 is minus, so it is, we get 3Z I1 is equal to this VBS minus VCP plus VBP minus VAS. 1 into 2, 1 into 2 means plus 2 VAS minus 2 VAP plus 2 VAS minus 2 VBP minus 2 VAP plus 2 VCP minus 2 VAP, it is A, it is AP, 2 VAP plus 2 VCP minus 2 VBS minus 2 VBS. So we get I1 is equal to Y by 3 into minus 2 VAP AP plus VBP plus 2 VAP plus VBP plus VCP, and then what we have got, So it is actually it is VCS, because this is VC. So this potential is VCS, this potential is VAS, and this potential is VPS. So we should write them. This potential is VAS because B1 is A phase, A1 is C phase, and C1 is B phase. So this potential is VCS minus ZI1 minus VAP minus ZI1 minus I2 minus ZI1 minus I2 plus VCP and minus V. So this is VCS. So it is VCS. So then here also it should be VCS. There was a mistake. VCS. So it should be VCS. VCS minus VAP plus VCP minus VVS. So it is VCS. So 1 into 2. So we are doing 1 into 2. So it is with 2 VCS. It should be 2 VCS. 2 VCS. VCS minus VAS minus VBS minus plus 2 VCS, right. So this is I1. So similarly we can write down the I2. Similarly I2 can be solved, y by 3 something I2 can be solved. Once we solve for I1 and I2, so then therefore from here I can say that IC is equal to I1. So I can say that ICS is equal. So now here the current is ICS. So the current is ICS. So that is equal to I1. Here the current is IBS, because no, this is IAS. Sorry. This is IAS, this is IAS, this is IAS, because this is phase C. So voltage is VCS, current is ICS, and this is phase A. B1 is phase A. So this should be VAS. There is a mistake. Should be VAS. Should be VBS. This should be VAS, this should be VBS. Because this is phase B, so then this voltage is, this terminal is C1, but it is denoted as phase B, so then voltage it would also be VBS. This terminal is B1, it is denoted at phase A, so then voltage is VAS and the current is IAS, and here this current is IBS. Now ICS is equal to I1. So we can write down that ICS is equal to I1, and then we can write down IAS is equal to minus I2, and IBS is equal to, IBS is I2 minus I1, I2 minus I1. So ICS is equal to I1, IAS is equal to minus I2, and this is equal to I2 minus I1. So once we get this expression of I1 and I2, so from there I get ICS is equal to I1, because IC is entering this point, so this is equal to I1. IAS is entering this point, so here it is ICS, here it is IAS, and here it is IBS. IAS is equal to minus I2, and IBS is I2 minus I1. So then therefore if this is IAP, so then therefore IAP is again is equal to minus ICS. IAP is equal to minus ICS, IBP is equal to IBP, it is IBP is equal to minus IAS is equal to minus IAS, and ICP is equal to ICP is equal to minus IBS, minus IBS. IAP is equal to minus ICS, IBP is equal to minus IAS, and ICP is equal to minus IBS. So, we have got these 6 equations. So, we have got these 6 equations. So, and again we write that ICS is equal to I1, IAS is equal to minus I2. So, IAS is equal to minus I2, IBS is equal to, we are just writing this I2 minus I1, and ICS is equal to I1. So, these are the 6 equations, and from this we can see that all these equations are representable as with respect to VAP, VBP, VCP and VAS, VBS, VCS. So, once we write them, we can similarly write down the Y bus matrix as we have done for the last case, as we have done for this last case. So, this is the way any given transformer can be modeled. So, similarly, instead of let us say YGY, you can have also YGD or maybe YD. So, by applying these same principles, we can always model any 3-phase transformer having the standard vector group. So, once we have this 3-phase transformer, so then therefore as these examples show, we really do not need to memorize these Y matrices. These particular Y matrices can be very easily derived from the very basic fundamental principle. So, once these Y matrices are obtained, so after that they can be used very easily in our fault analysis. So, thank you.